Welcome back to our series on probability theory. I'm Mark Ledbetter. This is lecture video 49, part B, and this is part 4 of our discussion on the functions of the normal random variables. Up to this point, we've covered the convolution formula, which looks at y equals x, or I should say w equals x plus y. Okay, so we can find the marginal distribution of w using this. And then we looked at the linear combination of independent normal random variables, the corollary about x bar, where they are IID because they're from a random sample, some examples. And we've also looked at the theorem which told us that x bar and s are independent, although we didn't do the proof because it's very tedious. But you can look at that proof for yourself. And we did we proved that this quantity has a chi-squared distribution with n minus 1 degrees of freedom, and that's going to be very important in the next semester. So to finish off this, we're going to look at an example, then we're going to look at student's t distribution, the properties of the t distribution, and a few examples there using the t table. So the first example, we're going to let x1, x2, x3, x4 be a random sample of size 4. So we have n equals 4, and this random sample says that xi are IID, independent and identically distributed, and it says they're from a normal distribution with mean 76.4 and variance 383. We want to find the distribution of u, sum of xi minus mu squared, quantity squared, over sigma squared, and w, the sum of xi minus x bar, quantity squared, over sigma squared. We showed these in the proof of the last theorem. We derived these quantities, and I wrote them out as results. So it turns out that u here has a chi-squared with n degrees of freedom. Well, n is equal to 4, so we put in the 4. And then w has a chi-squared with n minus 1 degrees of freedom, so n minus 1 is 3 in this case. And now we want to find the probability that u is between 0.711 and 7.79, okay? And remember that u has 4 degrees of freedom. Let's open up our chi-squared table and look at 4 degrees of freedom. And we were looking at 0.711 and 7.779. We want the probability u is between these two values, so we can use the CDF, and we subtract those two values to get 0.85. As you can see here, 0.9 minus 0.05 is 0.85. Now, for w, we want the probability is between 0.352 and 6251. Now, w has a 3 degrees of freedom, or it has 10 degrees of freedom, if I remember correctly. Or actually, we were looking at 4 degrees of freedom, and now we're looking at 3 degrees of freedom for w. I was looking at the wrong table. So we have, we want 3 instead of 4. And we looked at 6.251 and 0.325 or 352, and they're in the same column, so it's the same probabilities. It's going to be 0.9 minus 0.85. Or 0.05, I'm sorry, and that gives us an answer of 0.85. Now let's talk about a very important distribution. This is student's t distribution. So this distribution is probably the second most important distribution in statistics behind the normal distribution. We use it very frequently. And so z, let's say that z is a random variable with a standard normal distribution, and v is a random variable with a chi-squared distribution and n degrees of freedom. If v and z are independent, then the distribution of t, which is z divided by the square root of v, and it's divided by its degrees of freedom n, that has a t distribution with n degrees of freedom. Okay? And so the book gives the PDF of this PDF of this distribution here, and the proof is in the book. So please make yourself familiar with the proof. Let's talk about some properties of t. This is the graph of t. It's symmetric about, it's bell-shaped, and it's symmetric about the mean, which is 0. It looks a lot like a standard normal distribution, except the standard normal distribution is going to be thinner. It's going to have a higher peak in the center, and it's going to be thinner. And so the tails of the t distribution are thicker. And so if we look at the area in the tails, the area for the t distribution is going to be larger than that for the standard normal distribution. So another important property is that as n approaches infinity, then the t distribution converges to the standard normal distribution. Also, we have the expected value of the moments, so the kth moment. If k is greater than or equal to n, then this does not exist. So e of t cubed for n equals 3 does not exist because they're equal. Okay? Neither does e to the fourth, but e squared, e of t squared, does exist, and so does e to the t. Okay? So, if k is odd, so we're talking about e to the t to the 1, e of t to the 1, or e of t cubed, or sixth, or a fifth, or seventh, or what have you, odd, and it exists. In other words, k is less than n. So for here, n is greater than or equal to 2, then this exists, and it's equal to 0. And here, n is greater than or equal to 4, then this is equal to 0. Okay? And the even moments have this lovely expression. Okay? Again, k has to be less than n. So for e of t squared, n has to be greater than or equal to 3. And for e t to the fourth, n has to be greater than or equal to 5. Specifically, for n greater than 2, e of t, the mean, mu of t, is equal to 0. And the variance of t is n over n minus 2. Okay? Handy to know. The moment generating function of t does not exist. Okay? So we're going to let x1, x2, xn be IID normal with mean mu, variance sigma squared. Then the square root of x bar minus mu over s has a t distribution with n minus 1 degrees of freedom. This is very important. We use this result in introductory statistics all the time. And the PDF of x is given here, and it's in the book. Just recall that gamma of 1/2 is the square root of pi. So let's do some examples. We're going to let t have be distributed as a t distribution with 11 degrees of freedom. Now, the degrees of freedom are going to be n minus 1 in this case here, okay? But there will be different degrees of freedom based on n, depending on the application. We want to find the probability that t is between negative 1.796 and positive 1.796. It's always handy to draw a sketch. So negative 1.796, positive 1.796. And so the t-table only has the positive values here. Let me clean this up a little bit. And so we have 11 degrees of freedom. And we said we want the probability between negative and positive 1.796. And we see that the probability that t is less than 1.796 is 0.95. So from here, from here this way is going to be 0.95. And that means that this amount is 0.05. They have to add up to 1. Now, by symmetry, the area over here in this tail is the same as this area here, which is 0.05. And so to get the area in between that's not shaded, we subtract 0.95 and 0.05. And that's what we've done here, and the difference is 0.9. Now again, let T have a T distribution with 11 degrees of freedom. We want to find these three quantities. So the first one is that T is less than or equal to 2.201. So 2.201 is here, and the probability that we're less than that value is given by the CDF, which is 0.975. And there is the answer. Now, the probability that T is greater than or equal to negative 1.363. Again, a sketch will help us. Negative 1.363, and we said greater than. So that means that we would shade up here. And remember, zero's here. So there's no negative numbers in the T table. But we know by symmetry that if this is 1.363, that the area here is equal to the area here. Likewise, the area here that's shaded, these are equal. These two areas are the same. So if I look at positive 1.363 and look at the CDF, I'm going to get the right answer. So I look at, and I see that for 1.363, which is here, that the CDF is 0.9. And so my answer is going to be 0.9. Okay. Now, to find the probability that T is less than negative 1.363, then I can look at the unshaded portion here, and I know that this portion is 0.9 from the previous problem. So this portion has to be a 0.10, because again, they have to add up to 1. Now, if we hadn't done the previous one, this is a negative 1.363. That's going to be the same if I look at this, I want less than this, so I want this area over here. That's going to be the same as this area here, which is 1 minus the area to the left, or to the left of 1.363. So it's going to be 1 minus 0.9, which again is 0.10. And so there's two different ways to find that same answer. All right, so that's it for this lecture. I hope that's been helpful for you. Please don't forget to scan and upload your lecture notes before midnight of the date listed in the course calendar. If you have questions, come to virtual office hours. If you need an answer before you can make it to virtual office hours, email me, but send me a picture of your problem, because I may not have it handy, and a picture of your work so I can see how you're approaching the problem, and then I'll be able to help you more efficiently. Please take care of yourself and stay safe. We hope to see you next time.